We now discuss the solution of a problem from the section Complex Analysis. This question is on entire functions. This question has appeared in the CSIR National Eligibility Test held on 16th February 2022, and this question is from part C. The given problem is, let f be an entire function such that mod of z fz minus 1 plus e power z is less than or equal to 1 plus mod z for all z belongs to the complex plane. Then we are given four options. Option 1, f prime 0 is equal to minus 1. Option 2, f prime 0 is equal to minus 1 by 2. Option 3, f double prime at 0 is equal to minus 1 by 3. Option 4, f double prime at 0 is equal to minus 1 by 4. We are given f is an entire function and we are given this inequality, that is mod of z fz minus 1 plus e power z is less than or equal to 1 plus mod z, true for all z belongs to C. Then the four options are given to us and we have to find out which of them are true. We now discuss the solution of the problem in detail. We have an entire function f and it is given mod of z of z minus 1 plus e power z is less than or equal to 1 plus mod z for all z belongs to C. Now divide throughout by z. Then you will get mod of fz plus e power z minus 1 whole by z is less than or equal to 1 plus mod z by mod z, and that will be 1 plus 1 by mod z when z not equal to 0, that is same as for z belongs to C star. This implies we will write this as modulus of h of z less than or equal to 1 plus 1 by mod z for all z belongs to C star, where h of z is written as f of z plus g of z, and where g of z is e power z minus 1 by z. H of z is f of z plus g of z and g of z is e power z minus 1 by z. So let us now see what this gz is. Now g of z is equal to e power z by z minus 1 by z is analytic everywhere except possibly at z is equal to 0. Right. The numerator is an entire function. The denominator is also an entire function, one by the other. Then it is analytic everywhere except possibly at z is equal to 0. We now see the limit z tends to 0 of g of z. Limit z tends to 0 of e power z minus 1 by z. As z tends to 0, the numerator takes 0 value, the denominator takes the 0 value, and hence we get an indeterminate form 0 by 0. We use L'Hopital's rule. That means limit z tends to 0, the derivative of e power z minus 1 is e power z, by the derivative of z is 1. So limit z tends to 0, e power z, that is e power 0, that is equal to 1. We use L'Hopital's rule. So this means z is equal to 0 is a removable singularity of gz. It is analytic everywhere except possibly z is equal to 0. Now z is equal to 0 comes out as a removable singularity of gz. Therefore, it is analytic everywhere and hence it is an entire function. Therefore, h of z is equal to f of z plus g of z. F of z is given to be an entire function. Now we have seen g of z is an entire function. Therefore, the sum of two entire functions is also an entire function and hence h of z is an entire function. Therefore, h of z is equal to f of z plus e power z minus 1 by z, that is g of z, is an entire function. We continue in the next slide. We have h of z is equal to f of z plus e power z minus 1 by z is an entire function, and we are given f of z is an entire function. Agreed. Agreed. Now, this means we are given mod of f of z plus e power z minus 1 by z less than or equal to 1 plus 1 by mod z for all z belong to C star. This is the starting point. And this is hz. So, mod of hz is less than or equal to 1 plus 1 by mod z for all z belong to C star. Agreed. Now, we deal with two cases. Case 1. Let D is the set of all z belong to C where mod z greater than 1. That means it is the exterior of the unit disk. It is the exterior of the unit disk. Then mod of hz is less than or equal to 1 plus 1 by mod z. But in D, mod z greater than 1. Therefore, 1 by mod z less than 1. Therefore, 1 plus 1 by mod z is less than 1 plus 1, that's equal to 2, for all z belongs to D. That means mod hz is less than 2 for all z belongs to D. H of z is bounded in D. Let's see what happens in the case 2. Let D prime is the set of all z belongs to C, mod z less than or equal to 1. It is the closed disk, closed unit disk. It is the closed unit disk, right? And moreover, note down is the D prime is a compact set. Now h of z is continuous in D prime. Why? Because h of z is an entire function. Entire means it is differentiable everywhere. That means it is continuous everywhere. Since it is continuous everywhere, h of z is continuous in D prime. Agreed. Now h of z is continuous in D prime, where D prime is compact. So continuity and compact will imply boundedness. So h of z is continuous in the compact set D prime. Therefore, h of z is bounded in D prime. This is so because D prime is compact and h of z is continuous. So now h of z, combining these two cases, h of z is bounded in D, h of z is bounded in D prime, and D union D prime is the whole of the complex plane. Therefore, combining the two cases, h of z is a bounded in the whole of the complex plane. But what is hz? Hz is an entire function. Now it is bounded in the entire complex plane. So we recall the famous Liouville's theorem. Thus h of z is a bounded entire function. This implies h of z is constant, say C, by Liouville's theorem. What the Liouville's theorem says? Every bounded entire function is constant. So h of z is constant, let us say C, using the Liouville's theorem. So therefore, h of z is equal to f of z plus e power z minus 1 by z is equal to C, where C is a constant. We continue in the next slide. So that's what we have so far. Now that is equal to f of z. F of z is equal to C plus 1 minus e power z by z. Yeah, send this to the other side. So that is equal to C plus the numerator 1 minus in brackets the expansion of e power z, 1 plus z square by 2 factorial plus z cube by 3 factorial plus so on and so forth, whole by z. The 1 cancels. and z is a common factor both numerator and denominator, then you will get c minus z by z minus 1 minus z square by 2 factorial by z, that is z by 2 factorial, minus z cube by 3 factorial by z, that is z square by 3 factorial, minus z to the power of 4 by 4 factorial by z, that is minus z cube by 4 factorial, minus so on and so forth. That is your f of z. Now f prime z, you differentiate once, f prime z will be minus 1 by 2 factorial, yes, c minus 1 is a constant, minus 2z by 3 factorial, minus 3z square by 4 factorial, minus so on and so forth. So put z is equal to 0. F prime 0 is equal to minus 1 by 2, and the remaining all terms are having z. Therefore, when z is 0, all of them will vanish. So f prime 0 is equal to minus 1 by 2. Let's look at our options. Our answer f prime 0 is equal to minus 1 by 2 appears against option 2. Therefore, option 2 is true, and in option 1 it is given f prime 0 is equal to minus 1, but it is not. Therefore, option 1 is not true. Now differentiate once again this f prime z with respect to z. That means f double prime z is equal to minus 2 by 3 factorial minus 6z by 4 factorial minus so on and so forth. So put z is equal to 0. F double prime 0 is equal to minus 2 by 3 factorial, that is minus 1 by 3. And let's look at our options. Our answer f double prime 0 is equal to minus 1 by 3 appears against option 3. Therefore, the option 3 is true. And in option 4, it is given f double prime 0 is equal to minus 1 by 4, but it is not. Therefore, option 4 is not true. So the answer to this question, option 2 and option 3. And that is the detailed discussion of the solution of a problem on entire functions from the complex analysis. And I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.